So first of all, welcome to the Impact Scholar presentations. And the Impact Scholars is a 6 month initiative that brings together Neuromatch and Match students to collaborate in international teams on research projects that they started during our July courses. The program culminates with an open access micropublication that will be released on Zenodo, a public summary, and a seminar presentation. And today we're actually going to hear 2 of these seminar presentations. Each group, just like some rules or instructions about today, each group will have 15 minutes to present, which will be followed by 5 minutes of questions. And at the end, like after both presentations, there will be additional time for further questions if there are any. Our first presentation is from the Montrebia Cabinet Group, Computational Neuroscience, and their project is titled Working Memory Involvement in Higher Cognition, Insights from fMRI Modeling. So I'll now hand the stage over to them, and thank you everyone for joining.
Thank you everyone. Hello. Let me just share my screen first, and then we will begin the presentation. I'm hoping that you can now see my screen.
Yes.
Okay, perfect. So hello everyone. Thank you for joining us today. As you can see, the title of our work, as Viviana mentioned kindly, is Working Memory Involvement in Higher Cognition. And we will be discussing a method that we came up with, in essence, that helps us use fMRI data to model working memory and working memory involvement. So first, let's meet the team. This is our team. Unfortunately, we don't have everyone here today. Half of the team is present, and we had our wonderful supervisor, Dr. Rodriguez Cruces. And you can actually, if you scan this QR code, you can go to our repository on GitHub and find the links to each person from the team if you want. I will keep that up for one more second if you guys want to scan that. I will present it again at the end of the meeting as well. So if you miss it, we will be presented again. I will start by giving you an overview of the project. So our project, again, you can scan this to go to our repository, the main page. Our project generally talks about memory and working memory. Working memory is a part of the brain that deals with information that is needed for your current task. So for example, I am currently talking to you about our project. So all the information about the project is in an online state in my brain. That would be the work of our working memory. And through modeling, we decided to work on a sort of sensor, in a sense, that can detect high amount of information that working memory is working on, basically. So the higher the amount of information that I have to work on and I have to maintain online, the more my working memory is working. And the model that we have created is actually a kind of a sensor for that amount of information. And as you can see, let me turn on my pointer. As you can see, this is a working memory architecture and demand model. So the amount of information goes into the demand section, and the architecture talks about the location of working memory activation. So now I can hand it over to Barbara, and she will talk about the background for our project, and then we will proceed from there.
Okay, so our project is centered on working memory. It's a cognitive system that allows us to temporarily hold and manipulate information. And this system is essential for our high-level cognitive processes, such as reasoning, learning, problem solving, decision-making, language comprehension, etc. And the neural architecture of working memory remain a subject of debates. From the cognitive perspective, working memory has traditionally been conceptualized as a multi-component model. It highlights a centralized architecture with 4 subcomponents. Specifically, central executive, phonological loop, visual spatial sketchy pad, and the episodic buffer. And each component involves different brain areas and responsible for different functions. However, neurobiologicals perspective proposed a different model of working memory, which is dynamic neural resources model. This model conceptualized working memory as emerging from the dynamic allocation of neural resources across a distributed network, including subcortical areas. So according to this theory, working memory processes are not defined to fixed components, but it are adaptive and context dependent. So our question was coming, which theory explained working memory best? Then beyond working memory itself, the system plays a crucial role in emotion and language processing. Previous research has found the interaction between working memory and emotion, which mainly shows in the prefrontal and subcortical regions, including the amygdala, with the prefrontal cortex modulating emotional responses to ensure emotionally charged information is appropriate weighted without overwhelming working memory capacity. Then in terms of working memory and language tasks demand robust working memory resources to support complex syntactic and semantic operations. And their interactions mainly involve the subcortical structures and widespread right hemisphere regions. Based on these previous findings, we built our preliminary model, the multi-layer perceptron. Previous study has always used single task to examine the working memory involvement in emotion and language tasks, such as using the emotionally charged working memory tasks. So our project is different from them because our MLP model was trained by pure working memory inputs, and it has successfully predicted the involvement level of working memory in language tasks, which we will introduce it in detail later. However, our MLP model doesn't capture the temporary and relational patterns in fMRI data. So we aim to improve it to give a robust method to understanding working memory. So in a short summary, our study first worked on the GLM to get the activation pattern of working memory. This can provide a reference of mean task activation that could be potentially used to compare the working memory involvement of emotion and language subtasks. And the comparison is worked by our improved model with JNN and LSTM. And the main data set we used is from HCP, and it provided by Neuromatch Academy with the data of 100 health young adults. And we targeted on the subtask of working memory, emotion, and language in zero-back and two-back conditions. The 360 pulses and both signals are stored in pulsar-based both signals format.
Yep, yeah, we can take it over, Zep.
Yeah.
Go ahead.
In terms of the processing for that, we used we emphasized the use from the notebook that we got through NMA that we used on the preliminary project. This is the pipeline used for the current one. For the preliminary model, we flattened the time series out because it was just an MLP. But for this one, we had to process out the time series, managing and padding different lengths for some of the time series, and also producing an adjacency matrix and this target matrix structure, because we didn't just use the zero back versus two back labels like we did in the initial model, but we'll talk about that a bit more when we get down to that point of it. But this is the general pipeline that it went through. Had a series of helper functions which constructed the matrix, turn it into a tensor with the fMRI time series where it goes by all exposures, 360 parcels for the glass of parcels, along a time dimension. And the adjacency matrix was essentially a covariance matrix based off of the time series. And the target matrix is like the labels, essentially, but they're for each parcel and their activations, but only for the 2x tasks. But yeah.
Yeah, thank you. So the preliminary model we created during the summer when we went through the computational neuroscience course, and our results were a little bit exciting, a little bit too exciting at times. So if you look at the data, we can see that it can clearly distinguish fear, math, and story, but it is a little bit indecisive in terms of neutral predictions. However, these plots are not really exciting because, first of all, 2 bins at the top is a little bit misleading. And then the bottom plots are a little bit boring in terms of color and also a little bit questionable in terms of their axes. So we decided to throw this away and do a 3D model. So you can now see that, first of all, the neutral predictions in the front, they're basically 50-50. So we cannot really interpret anything based off of that. However, for math, fear, and story, we can see a clear distinction. And the reason that math and story are higher in terms of their prediction frequency, is because in general, we had more data for math and story compared to emotion subtasks. So this data from the preliminary model showed us that we can rely on this model to be able to distinguish between high demand and low demand for other tasks compared to working memory when it is trained on working memory. Then we can talk about the structure of the model. So we realize that the model is very much reliable. This is how we kind of started to do the structure for the model. Parcel-based bold signals averaged were input into a multi-layer perceptron, as Barbara told you, and these have dense and dropout layers. And then it reached at times higher than 90% accuracy, but if you want to be a little bit conservative, we can say 88% accuracy when it was predicting working memory involvement. So structure of the model is a funnel shape for feature extraction, and it has dense and dropout layers. And while it performed well, as you can see over here, there are limitations to this model and there are reasons for its improvement. So the first one is data, of course. We only had 100 subjects, and those subjects had averaged bold signal. We did not put in time series. And the output was paired. So the model was only producing either a 0 or a 1 as a probability. So the probability number for the task or the exposure being 0 or 1. And the architecture, as I mentioned, is super simple. And finally, interpretability. We didn't have enough information on parcels or decisions that the model was making. So we had to improve the model. Zeb can take over. Yep.
So this is the present version of the architecture, which is a rather crazy version of it. So essentially we added components for a GNN aspect and an LSTM aspect to try and capture these different dependencies. It still concludes in the MLP architecture at the end, but it just has these different inputs. The GNN is what takes in the adjacency matrix and also takes in fMRI, trying to learn relational dependencies. The justification for that being we could have used something like a CNN, but that only accounts for spatial neighbors. But considering it's connectomic data, it's interesting to try and capture the wider sort of breadth of that. So we used a GNN and explored that in a few structures. We did have an initial model of this, which was more sequential, where it went GNN into LSTM into MLP, but we had a lot of problems. I'll discuss a bit of that after this slide. But the main thing with this is it has these two aspects. The masked matrix. So just go to the next slide.
Yeah, sorry about that. Oh, I haven't updated it, so give me a second. Sorry. Yeah. Hold on,
I
sorry.
thought it was the live one.
Yeah.
Sorry, Vivian, I threw some extra things while we were talking.
No
Yeah,
problem at
technical
all.
difficulties.
Yeah, that's
Sorry about
normal.
that. Okay, I think we have it. Okay,
Very
let's.
clever.
Yep. All right. We should have it now. Okay.
So this is the target matrix. So this is one of the things that was different. So as opposed to it just producing either a prediction for 0 back or 2 back, so high load or low load, each parcel, if it passed a certain threshold on the 2 back task, had an activation, and we had that for every parcel. And we set the model up in such a way that you could choose which parcels to have as the emphasis that would come as the outputs. Initially, we were trying to train it on all 360. That definitely did not work. There was way too much sparsity for that to function appropriately. In the end, after we did some tuning, it kind of came out to 3 was pretty good. And the ones we ended up using were the one of the ACC left, I think, and 2 of medial DLPFC components left and right. They seem to go pretty well by the end of it. But even then, sparsity was a bit of a problem here. This is the target matrix sort of illustrating it and sort of the activations across it. The way the model, it would essentially mask out which aspects of that weren't getting chosen for as training data. It would still take account of the overall covariance matrix of the overall data set, but it would just only use those as outputs. The next slide will have the actual convergence rates that we had in the end. Not as clean as it was with the MLP, admittedly, because we trained it in like sections. So we trained the GNN, the attentional GNN in one section, then trained the LSTM, froze those, and then trained the whole thing as one big series. And this is the output for that part of it. Loss is still not bad. It kind of sort of wobbles around a bit. In terms of the precision versus recall, it doesn't seem to vary a lot. There was a lot of problems where we couldn't get the precision into a good place early on. But this is where we kind of got to in the end. In the end, it kind of had an accuracy of around, I think 78 was the result at the end there, with an F-score of about 40. So it was performing quite reliably at that point. And then the next slide are kind of some of the preliminary results. A little bit hard to interpret. It's just, it very much weights towards 0 activations, but you can see that there is some differences between some tasks for different labels or different parcels.
Yeah. Okay, Barbara, you can take over for the GLM.
Okay, for the GLM, we first built the first level GLM for each subject based on 2D metrics. One is the event-based design matrix, and another is the parcellated board time series array. Because our imaging data was not stored in Nifty files, so we have to do this with 2D metrics. Then we set contrasts to compare the activation of 0 back and 2 back conditions. However, we got stuck here because the built GLM was in a tuple structure, which is unusual for the GLM model with fMRI data. But this is not an error, and this issue will be solved in our new data, which is with neuroimaging data in Nifty format. Yeah.
Okay.
So let's move on to the discussion.
Okay, so I'm gonna, because I know we are a little bit limited on time, I'm trying to wrap this part and just go super fast. So what did we find? The first thing that we found is that, first of all, the model works. So we can train on only working memory data and apply that to other forms of fMRI tasks, so emotion or language or possibly other tasks. And then what could this mean is that we could potentially get various forms of fMRI data or even just MRI data, which is structural, and apply working memory models that act as sensors so that they will find high demand or low demand for tasks, or at times find normal versus abnormal working memory function. There are limitations, as we mentioned. One of them was the fact that the data is not as high in population as we would like. The other would be the fact that the NIFTY files were not available to us as high quality as we wanted them to be. So the GLM was not really viable at that point. And also the fact that the data is sparse, so our model is having difficulty being trained, although we did a lot of tuning. So future directions based on limitations would be to improve the input, obviously, use the whole HCP, improve model architecture. We did try sequential models and parallel models. Parallel ones performed better, but maybe sequential models as is being used in other studies will be more beneficial. Validation, we unfortunately did not have access to other data sets in this limited time to be able to validate our results. That is a major plan for our upcoming work, and also adding behavioral data. We did prepare behavioral data, but because the model was struggling to train, we couldn't really input the behavioral data for extra interpretability. Sorry about that. And also the population, which I mentioned. So the question is, why did we do all of this? The point is that when we have working memory, which is essential for problem solving, learning, and our memory, and we know how normal, healthy working memory works, we can apply that knowledge to other forms. So if we know how normal working memory works, we can use resting state fMRI from patients, potential patients, to see if they're working normal or they have neurodevelopmental or neurodegenerative issues. This vastly will be applicable to fields of cognitive rehabilitation and also education for special needs students or for rehabilitation of stroke patients, cognitive impairment patients, and all sorts of neurodevelopmental and neurodegenerative issues, including problems with learning. So that is the major thing that we have to consider, is that such a sensor will be applicable in various fields. Thank you for your attention. These are our references, and these are supplementary materials, but for now, this is the QR code for our repository again, if you want to check it out, and we commence the Q&A section now.